but it's okay. It does work. All right. So we are almost ready to talk about resolution. Well, we talked about resolution already, okay? But what we have not talked about are the other pieces that makes it useful. So we talked about CNF, conjunctive normal form, and how to transform any general Boolean expression into CNF. And your homework assignment is about that. So are there any questions about the homework assignment? Okay, does that mean that you guys don't have any questions, or you have not started?
I just started and have questions to you during your office hours. No, that's really what I'm doing.
I did not ask that out of being judging. I was just curious. Is it because nobody has looked into the homework assignment, or because you looked into the homework assignment and you got it done and there's no question that you have to ask? It is difficult in terms of there's a lot of chore, a lot of details to it. Yep, and then you have to clean it up. Yep. Well, you don't have to clean it up. If you leave it not cleaned up, I will still consider the answer correct. But it becomes increasingly difficult to keep track of what you're dealing with if you don't clean it up. So cleaning up is helpful because of that. All right, so I really like this table of content thing because it allows me to go straight to the topic that I need to go to. But I'm only doing this for the modules that I'm touching, and I'm regenerating the HTML documents. So the old ones will still be kind of not, so they still do not have a table of contents. All right, so today's main topic, okay, or at least the starting topic, is proof by contradiction. And most of you have at least heard of the term proof by contradiction. So the question is, okay, 1, what is it? 2, how does it work? And 3, how does it fit within the topics that we have been talking about concerning propositional logic? So those are the questions that we'll try to answer today. Yes?
No, go ahead, actually.
Are we recording?
I was gonna. No, you said.
Yes, we are. Okay, so we're recording and the audio is on. So I want to double check and make sure too. Okay, so we'll take a look at this derivation first. Okay, so this derivation is a subpart of the proof of how proof by contradiction works. So so we're looking at a whole bunch of implications. So we are looking at the implication of P implies Q implies, in big parentheses, P and R for some R implies Q and R. Okay, this is what we want to prove. In other words, if you start with something simple, okay, okay, let's say taking text class implies you won't have any free time in that semester. Okay,
Pretty close to the truth.
so now we're going to say, if that is true, okay, does that imply taking text class and okay, I have to think about what R, what is a reasonable R to be ending with. Okay, taking text class and
What's the implication?
having a good time. Okay, taking text class and having a good time implies that you won't have time in that semester and having a good time. That's the question. Okay, is this implication, this counter implication here, does it hold? That's the question. Is that okay? And you can see that what we are trying to do is to say, I'm just going to pick some random expression R, random independent variable R, and we just say that can we just randomly pick something and add to the implication on both sides? That's all it's asking. Is that okay? So the proof of this particular implication is the rest of this derivation. So we'll go line by line just to make sure that we know how it is derived. From the first step to the second step, all I did is to turn the inner implications into the negation of the first part or the second part. Same thing over here. So we are basically saying it is the negation of the first part of this implication or the second part non-negated. So are we okay with this part? Okay, I'm just using the definition of implication, but in the inner implications. And then the next one is applying to the outer implication. So we negate this part here, and then we do an OR with the entire right-hand side of the outer implication. Is that okay?
Definition of implication.
And once again, it is the application of the definition of implication, but this time applied to the outer implication. So I separate these into two steps just so that it is kind of obvious, what I'm doing in each step. From here to here, I'm applying De Morgan's law. Okay, so De Morgan's law is applied to this one here, so that we have we distribute the negation to P, the negation of P, and also to Q. But because now we end up with double negation of P, they cancel out. We just get P back, and the negation of Q is the negation of Q, and then the operator has to change from a disjunction into a conjunction because of De Morgan's law. Okay, so that's the application of De Morgan's law. On the other side, I am not doing much other than removing the extra parentheses that is not needed because disjunction is associative. Is that okay? So are we still doing okay so far on the fourth row? Okay, so from the fourth row to the fifth row, what do you think I did? I apply associative rule again, remove this pair of parentheses because they're all OR. Okay, and that's about it. What I did from step 4 to step 5. From step 5 to step 6, I'm using that trick again. Okay, I'm using that trick of introducing an identity in a conjunction, and this one I just leave alone. Okay. And then the one, which is the identity of conjunction, is turned into Q or not Q or not Q here. Yep.
You called it the identity of conjunction. You say 0 is the identity of disjunction?
Yes, 0 is the identity of disjunction. It's just like 0 is the identity in arithmetics to addition. Huh?
I just wanted to catch the term.
Yep. Now, if you take abstract algebra, they would use that term a lot. What is the identity of a particular operator? I'm gonna close the door. Oh, thank you. Yeah, the problem with these classrooms is it is too close to the parking lot. So sometimes you have some with a really nice bass speaker, and it just shakes the whole classroom. All right, so the one here turns into Q or not Q. This one turns into Q or not Q. Okay, tricks that we have done before. And then the next line between this line and the next line, I'm just using distribution. So we are distributing P or not Q, Q or not Q, to not P. So now we have not P and Q, not P and not Q. And then the same thing over here. Okay? And then from here to here, I rearrange things a little bit. I'm just moving things around. Okay, so I move this guy all the way here. I move this guy over here. And then same thing, I move this over here. Oh. Nope. I changed the order within the parentheses, just so that it's easy to identify what we can factor out. So and this one moved here, this one is moved here, and then within the parentheses, I also changed the order. But basically, they're using either the commutative law of these operators. I think they're only using the commutative law of these operators, which means you can switch the ordering of the operands without changing the meaning or the value of the operation. Is that okay so far? Okay. So the next line is doing the simplification because, okay, I think I skipped a step here. I skipped the step of factoring because when you look at the Q, okay, see how this Q is in this particular conjunction and Q is also in this conjunction. So I'm doing the factoring so that the in-between step is you end up with Q and then in parentheses not R or R, which then becomes a identity here. And then the same thing over here. Basically, I look at not Q and not Q here. We can factor that out, and then we end up with P or not P which then becomes this 1 here. And once we get to this point, I skipped one step again because 1 and not q is just not q, q and 1 is just q, so you end up with not q or q, which is 1. And because this entire thing, the top level operation is disjunction, that means if any term turns into a 1, the whole thing becomes a 1. And that's why we end up with this 1 over here. So that's kind of how I use Boolean algebra. This may not be the only way, definitely it's not the only way, may not even be the most efficient way to prove this, okay? But it is a way to get it done, okay? So what do we have at this point? All we have proven at this point is if you have some kind of implication, you can add, using conjunction, you can add some other term to each side of the implication without changing the meaning of the whole thing. If the original implication is true, then you can add some conjunction to something as long as you're adding the same term to both sides of the implication, that implication will still be true. Is that okay? It's kind of cool because this allows you to randomly add stuff to implications that are known to be true. Okay, so now what do we do with this? And by the way, this is how we do proofs, in one particular way. The other way to prove this theorem, guess what? Is to use something that we have talked about many, many times. Truth table. You can use a truth table to prove the theorem. What do you think the truth table is going to look like? You got 3 independent variables, P, Q, and R. They are all independent, which means you end up with 8 rows of values, right? So then you evaluate this entire expression, and it's going to come out as 1 for every single row. That will basically show that this entire expression here is always true. Is that okay? Yep.
So similar to what we did last time, where you change the concept 1 into Q or not Q. If we choose something other than Q, do we arrive at the same?
You may or may not. The reason why I chose to expand this one to Q or not Q and this one into Q or not Q is because we got Q's over here already. And I know that I need to annihilate P, as a term. So I need to somehow, introduce a Q over here so that I can combine this not P with this P to get rid of the P. So I kind of have a general direction that I know where I'm heading when I introduce the extra terms like turning the 1 into Q or not Q. Is that answering the question?
I think so. Well, I'm just kind of curious whether or not if you chose P or not P, whether that would be the way to eliminate Q instead of P.
You can give it a try. I mean, definitely. As I said, there are multiple ways to prove this theorem. This may not even be the quickest way. I mean, there may be ways that will involve fewer steps. Okay, that's possible. The truth table is the other way to prove a theorem in Boolean algebra, which means you just enumerate all the possible cases. If every single one is a 1, then it is a theorem. It is true. Yep.
So are we allowed to use truth tables if you were given an exam, proof by contradiction or whatever? You can do a truth table for the Boolean.
If I specifically ask for proof by contradiction, then you have to prove by contradiction. So the truth table way of proving something is not by contradiction. It is just by enumerating every single possible case, and then you look at the last column and go like, see, for every single possible case, this expression is telling me a 1, so it becomes a theorem. That expression itself is true all the time. Okay, so you have to read the questions carefully in the next exam and see what kind of proof technique I want you to use in that question. Okay, so now we're going to look at this part here. So now let's make a conjunction of all the known to be true well-formed formulae. And basically psi is the conjunction of all the well-formed formulae known to be true in the iota. Okay, so when you read this symbol here, let me magnify a little bit just so that we can see a little bit better. Okay. Okay, I think I lost track of where I was. Oh, the other way. Scroll down. Proof by contradiction. There we go. Okay. Okay. So we are focusing on this definition of psi here. We are looking at every single element of I, basically, and then we say, okay, make one big gigantic conjunction of everything in iota. Now, if something is in iota, it is something that is known to be true, right? It's given to you. This is true. Don't ask me why. So if I make a conjunction out of those things, that just becomes psi. Okay, so psi is just a representation of everything that we know to be true, and it is a CNF. It's a conjunctive normal form. Is that okay? Any questions about that part? Okay. And then we now use phi as a symbol to represent a theorem. Now a theorem in this context is nothing more than a well-formed formula. Okay? And the question is, can psi, which is everything that is known to be true, can that imply phi, which is our theorem in question? That is the question. Is that okay? Are we clear on those terms? What psi is, what psi is representing, and what phi is representing? So this implication is a question mark. Okay, we don't know whether that implication holds or not. Okay, we hope it does. Okay, but there's a chance that it does not. So we want to prove a theorem, and now we look at this derivation. Okay, so we're basically saying, okay, let's just say that phi is a theorem. Okay, so that psi implies phi. Is that okay? We are making the assumption that it is a theorem. So this implication here is making use of the theorem that we just established. In other words, I'll just add a conjunction to each side of the implication. That should be okay, right? If the original implication is true, then if I add that, that implication should be true as well, right? Okay, but the additional term that I choose to add using conjunction is really tricky. I'm choosing to add the negation of phi, the negation of the theorem that you want to prove, to make it ended with psi on one side and phi on the other side. Is that okay? I mean, if you look at the theorem earlier, nobody says to me what R cannot be. R can be anything because it can be just any other. It can be any independent variable that is not P or Q. Okay, so when you look at this, then you look at this part here. It looks suspicious, right? Because we got phi and not phi here. What do you think phi and not phi is going to be? It's always going to be false, right? So this in return implies this following, which is saying, okay, so psi or not phi implies false. But we know this implication is going to be true. So what can this possibly be? So what makes an implication true? Tell me again. In the truth table, okay, what makes an implication itself true? So let's.
Everything as long as the first one is false and the first one.
Except for that row, right? Everything is true. Okay. So let's take a look first, because I do want to kind of look at that truth table and point out which row is important to us at this point. Okay. So we're looking at x, we're looking at y, we're looking at x implies y. Okay. 0, 0, 1, 0, 1. Yeah, here's another one. 1, 0 is the only case when you have a 0 here, and then 1, 1 is a 1 as well. So that's the truth table of implication. Okay, when you look at this part here, we know that the second part of the implication is a 0 already. In other words, we are looking at these two rows. Okay, we're basically saying, okay, we know what we are implying is false. Okay, but we want the implication itself to be true. Do I really have a choice here? I don't have a choice. I have to choose which one. The first one, right? So that means if I know that what I'm trying to imply is false, then what I start off with has to be false. So the conclusion is when you combine everything in iota and the negation of a theorem, that has to be false. And that's where the contradiction is. The contradiction basically means when you combine everything that is known to be true and the negation of the theorem, what you think may be true, but you negate it first, that conjunction will lead to the constant false. That is proof by contradiction. Is that okay? So to utilize proof by contradiction, you have to identify these two pieces. What is given to you? Okay. What do you know? What is told? What are you told to be true? Okay. These things are told to be true. What is the theorem? What are you trying to prove? Because you have to negate that part, and then you make a conjunction between those things, and then you just have to reason it out and go like, why is this impossible? Why is this always false? Is that okay? So this is okay. So let me switch back to the browser. This up to here, okay, and including that smaller theorem, this is the proof of proof by contradiction. It shows that proof by contradiction as a method works. It makes sense. Are we doing okay so far with this example? Sort of? Maybe? Yep.
For this one, if you want to do a truth table from each row that you did or each line, you have to set a truth table for that line.
You mean to prove this one?
So psi implies 3. You have to do a truth table for that one, and then a truth table.
You can use a truth table technique as well. Okay, so you can use a truth table to show that every single row of this is false, but it has to be every single row because we want this entire conjunction to imply false. And anything that can, there's only one thing that can imply false where the implication is still true. It is false itself. So that's why basically you can use a truth table and make use of proof by contradiction, but then you're looking for basically every single row to end up with a false. Is that okay? All right. So we're good? All right. So are we convinced that psi is easily a CNF, easily a conjunctive normal form? Can you guys buy that? Yep.
Sorry, I guess for me the confusing thing about that is that for you got phi, right? The second one for phi, right? But it seems like if you're saying that's any theorem that's not an iota, then the contradiction of it, like the
negation of that,
is always, let's see, the negation of that is always going to lead to a contradiction.
The negation of the theorem, conjunction and everything else that is known to be true will lead to false.
Okay.
You can have only a conclusion of nope, that is not possible. Okay, so let's go ahead and do one example, okay? Because that's how we can actually get to see proof by contradiction works. Okay, so let me switch to my tablet because I'm just going to free form write something here. So go to Visor. Yep, it's working. My hard drive is blinking. It's just really, really slow. Okay. Find. Okay. And we switch to lecture notes. Make sure that we're in the right class. There we go. And open a new slide. There we go. Okay. So I want to prove something that is useful in its own way. Okay. So the question is whether a number is prime or not. Okay. 101. How do you know 101 is a prime number? But how do you know that it's only divisible by itself and 1? You have to try, right? You have to try to divide it by 2. Okay, it's not divisible by 2. Try 3, it's not divisible by 3, and so on. So now the question is, when do you stop?
When you get to the previous prime number.
When you get to the previous
Prime number.
Which is 97, I think, right? Do we have to go that far?
Isn't it when you stop at the square root of whatever you're trying to?
Exactly, we can stop at the square root, but prove that, right? Prove that if a number has a factor, when you talk about the factor, you can talk about the other factor, the way when these two numbers multiply, you get the number back. So I'm saying that if a particular number p can be expressed as the product of ab, then a or b is less than or equal to the square root of p. That's what I'm claiming. Okay, so I'm going to write it down here. Okay, so the theorem is basically saying, so let's say a, b, and p are all elements of natural numbers. Okay, so we're only dealing with natural numbers here. If I tell you that p is the product of a times b, okay, if this is told and known to be true, then it implies that a is less than or equal to the square root of p, or b is less than or equal to the square root of p. Okay, I'm just adding extra parentheses to make it very clear what the theorem is about. Is that okay? Now, I know some of you are saying, okay, what about the quantifier? What should we use as a quantifier? You can always say for all a, b, and p in the natural number set. That's the quantifier. In other words, go to the natural number set, pick out any 3 elements. Okay, I don't even care which 3 you pick. If p is the product of ab, then I can guarantee you that a is less than or equal to the square root of p, or b is less than or equal to the square root of p. That's the theorem. Is that okay? It does make sense, right? Okay, you pick any natural number, and it seems to be true. You can pick something that's tricky, like 49. Okay, 49 is 7 times 7. Okay, well, 7 is less than or equal to 7. 7 is less than or equal to 7, so the disjunction is definitely true because both sides are true. You can pick something that is kind of lopsided. Okay, let's take 21. 21 is 3 times 7. 7 is not less than or equal to the square root of 21, but 3 is. Okay, you can even pick a prime number. Okay, 101. 101 can be expressed as 1 times 101. Obviously, 101 is not less than or equal to its own square root, but 1 is. So it seems like we cannot find a particular case to prove that this theorem is wrong. But just because you cannot find a counterexample doesn't mean the theorem is true. Now, the opposite way is true. Okay, if you can find a single counterexample, then the theorem is false. But you cannot say, I cannot find a single example to show this theorem is false and therefore it is true. That doesn't work. So we want to prove this by contradiction. Okay, this is actually a pretty good application of proof by contradiction. So now we're looking at the negation of the theorem. what does it look like? What does the negation of this theorem look like? Well, I can tell you what it looks like. It looks like this. The negation of, for all A, B, P in N, P equals AB implies, okay, I'm going to change the format a little bit. A squared is less than or equal to P, or B squared is less than or equal to P. Is that okay? Because I just don't like to use the square root of, unless we absolutely need to use square root of. Is that okay? Because because they're all natural numbers, right? So the square, using the square to get rid of the square root works just fine. Are we buying this? Okay? The negation of the theorem. So now we need to somehow work that negation into the inside until we get to something that is usable to us. Okay? How many people still remember how we negate a quantifier? How do we move the negation so that it does not apply to the quantifier itself anymore? It applies to what the quantifier is quantifying. Do you guys remember that? Yep.
I actually have a question about which row. Don't you need parentheses?
Am I missing parentheses?
Yeah.
Oh, I'm missing one. Okay. There we go. Okay.
No, that's not what I mean. You need a set of parentheses, so you need one more in front of A squared.
One more in front of A squared. Maybe here.
Yep. There you go.
Okay. Okay, so are we okay so far with this? So now we want to move the negation. Instead of applying the negation to the quantifier, we want it to apply to the inside. So this is kind of like De Morgan's law, but it's not. Basically, you turn the for all into there exist. Okay, when you move the negation to the inside. So now we are saying, okay, if the theorem is false, then there should exist three numbers, A, B, and P. But we want to make sure that these things are also from the natural numbers. Okay. But now then we negate whatever is inside. So we say it is not the case that P equals AB implies A squared is less than or equal to P, or B squared is less than or equal to P. Close that, and I think that should be it. Okay. Is that okay? You can see how I just moved the negation from here, which applies to the quantifier itself, to here, which applies to what we are actually expressing after the quantification. Is that okay? But we know how to do this. Okay, this negation here applies to a implication. So we're going to look at the implication and go like, okay, how do we negate that? So for all A, B, P in natural numbers, it is not the case, okay, that I'm going to do a few steps combined, just so that we save a little bit of time. So it is not the case that P does not equal to AB, or the following is still the same. A squared is less than or equal to P, or B squared is less than or equal to P, like that. Would you buy this? I skipped a few steps, okay, because I'm using the definition of implication, where it negates the first part and then it ors the second part. But when you negate the first part, okay, the first part was P equals to AB. When you negate it, you can say it is not the case that P equals to AB. But the easier way to say that is P does not equal to AB, right? So that's what I'm doing here. And then I'm dissolving the parentheses of the second side, of the other side, because now we just have ors and it is associative. So we don't need those extra parentheses anymore. So is that okay? Are we buying this? So now we need to move this negation to the inside, which means we have to apply De Morgan's law. Now, as it turns out, De Morgan's law is scalable, okay? In other words, when you have multiple terms, but they're all combined using a disjunction, it applies the same way when you apply De Morgan's law, okay? So that means now we end up with there exists A, B, P in N such that P equals to AB again, because now we're applying the negation to the equality,
and a squared is greater than p, which is the negation of a squared is less than or equal to p, and b squared is greater than p as well. Is that okay? Does that look like De Morgan's law to you? Just apply to 3 terms in the operator instead of 2. Are we cool? Yep. Okay. All right. So now we can just kind of forget about the quantification, okay? Because the quantification is just saying that, yeah, we can find at least one case to make this thing true. So now we have to say, no, you're not going to find this to be true. There's no way that you can find A, B, and P from all the natural numbers to make this true. That is what we want to get to. So when you look at this part here, what kind of derivation are you going to use to make a contradiction, to say that, nah, this cannot be the case? Because we want this to eventually boil down to a 0, right? So we want to look at, okay, what can we imply? So let me rewrite this over here. P equals to AB, and a squared is greater than P, and b squared is greater than P. Okay. Now, because P equals to AB, right? What if I want to square P and square AB? That equality should still hold, right? Because if you square both sides, then the equality, that should always hold. Okay. So I can say that this implies that P squared equals to A squared B squared. I mean, you don't need the entire conjunction, just this part implies that. Is that okay? That's just normal algebra, not Boolean algebra. Is that okay? But that also implies one more thing, doesn't it? Because now that we know that P squared is A squared B squared, and we know that A squared is greater than P, and B squared itself is greater than P, what do we know about P squared? We know that P squared is greater than P squared. Is that making any sense? Well, I mean, it's better to write this as less than, because we are looking at A squared, B squared being greater than P squared. But you get the idea, right? Just this by itself is impossible. But the implication itself, it means this whole thing is not possible. It means that whatever we start off with, this conjunction is false. Because the whole thing implies false. And there we have our contradiction. So the contradiction is basically saying the negation of the theorem is impossible. Well, then what else has to be true? The original theorem has to be true, because the negation of the theorem is impossible. Is that making any sense? Yep. Yes, you basically say that, let's say this is a theorem, okay, let's say this is true, and then the steps to use proof by contradiction is to negate the theorem first, and you combine it with everything else that is told to be true, that you were told to be true, and then see how that can lead to false. That's proof by contradiction. Yep.
So in the last part, we're saying that the first part of the implication is true, right?
Say that one more time.
So the first part of the implication is true.
The first part of the implication, which part are we talking about?
So no, I'm going down. P equals AB or
This part here?
Yeah. So
Okay,
that's-
so this part here, okay, let me choose a different color. This entire part is basically derived from the negation of the theorem. Okay, so the negation of the theorem leads us to the conclusion that there exist 3 natural numbers, A, B, and P, so that P does equal to AB, and A squared is greater than P, and B squared is greater than P. It is a consequence of the negation of the theorem itself. Is that okay? But this, because of algebra, because of normal algebra, it implies that p squared is a squared b squared, because you can square both sides of the equality without changing the truthfulness of the equality. But at the same time, because we also know the inequalities of a squared is greater than p and b squared is greater than p, now we can say, oh, so that means a squared times b squared has got to be greater than the other side. But AB itself is P. So now we're saying AB is P, AB is P. So now we're saying we are saying P squared is greater than P squared itself, which is not possible. Is that last part okay?
I understand what you're saying. I was just looking at it differently.
Okay.
Thinking as in implication.
Implication?
The first part. If the first part is false, then and the second part is false, so the implication. Right? So if something implies false is true.
Yes, the only way that something that implies false is true is for the first part of the implication to be false. Yep. And that's how we know that this portion has to be false, which means the negation of the theorem itself has to be false. And therefore we have our contradiction. Is that okay? Yep.
Just to be clear, the second last step there about that box, where we're removing the negation, that's an application of Morgan's law.
Yes, that is. So from here to here, it is the application of De Morgan's law. It just applies to 3 terms inside the disjunction, but it works the same way.
Yeah, we're the same.
Yep. Yep. Switching, you mean here? From here to here? Yes, because you're applying this negation to the less than or equal to. Not less than or equal to is the same thing as greater than. So that's how that's how I simplify it. If I do not simplify the kind of negation on the outside, then this will still be less than or equal to. So are we okay so far with this derivation, or as an example of proof by contradiction? Sort of. It's a really powerful proof technique, by the way. It is actually much more powerful than direct proof. Okay? So are we cool with this? Okay. So if we're cool with this, then we are going to go back to nope, you go away. We go back to the browser, and we want to find out how this is going to help us in propositional logic. Okay, so the general strategy, this is the combination of everything that we have talked about in this particular module. So the first thing we want to do is to convert everything in iota into a CNF, into a conjunctive normal form. And that should be pretty easy to do, because the only thing inside, because we're using a new qualification of what is well formed, everything in iota has to be either a single term from alpha, the negation of something from alpha, or a disjunction itself. So when you're looking at a conjunction of all the disjunctions, it is in CNF, it is in conjunctive normal form already. So the first step, convert all Boolean expressions in I so that the overall system is a CNF. We can get it done. Okay? We know it can be done. The second step is to look at the theorem, the well-formed formula, or just the Boolean expression that you want to prove. You look at that, you negate it, and then you convert that also into CNF. Okay? So you got one CNF from everything that is known to be true, all the stuff from iota. You have another CNF which is representing the negation of the theorem that you want to prove. Is that okay? And based on proof by contradiction, when you use a conjunction to combine the first CNF and the second CNF, that should lead to a contradiction somehow. Is that okay? So now the question is, how do we get there? we apply resolution until everything resolves to a 0. Is that okay? It's not okay. You're not supposed to say it's okay, because if you say it's okay, then I have no need to write the rest of the module. Okay? So you're supposed to understand the general idea of, we are making use of all of those things that we just talked about. Conjunctive normal form, which is nothing more than another way to express Boolean expressions. Okay? Everything looks like a huge conjunction, and then each term of the huge conjunction by itself is a disjunction, but you can only have things from alpha or the negation of things from alpha in the disjunction. That's CNF. Okay? Your current homework assignment is to show that, yes, we can convert everything. Every Boolean expression can be converted into CNF. That's the whole piece about CNF. The second piece of negating the theorem first is proof by contradiction. And we just did an exercise of proof by contradiction in general to show that that technique is indeed quite useful. Okay, so that's the second piece. The third piece is resolution. Okay, resolution is basically saying, okay, given that these things are true, what can we imply that is also true as well? Okay, so by using resolution, at some point, okay, if there's a contradiction, we should get to a 0 in the entire term. Now, because when you apply resolution, you're adding terms to a huge conjunction. So if you get to a single 0 in the entire conjunction is false. Does that make sense? Okay. All right. So now we're going to look at 2 examples. So the first example is this is our this is what is known to be true. I'm using the same symbol, psi, to represent what is known to be true. This is given to you. We know this is true. Don't ask me why. So in this case, what is known to be true is, for whatever reason, not P or, and then in here we have the negation of R implies Q, and P or T is known to be true. Okay, don't ask me why. We just know it's true. So it can be expressed in CNF as this. Okay, so do we want to go through that exercise and find out why it can be expressed as simply not P or R and not P or not Q? I think we might have gone through this example before. Yeah, so this is actually coming from one of the examples that we had earlier. So I'm not going to go through that whole exercise again, but we know that we can convert this. This is from earlier. And the derivation from earlier is actually mostly step-by-step anyway. So you can actually go through that exercise if you want to convince yourself that this expression can be, the equivalent form is this, but it's a CNF. Is that okay? Cool. All right. This is new. Okay, this is my theorem. My theorem, represented as phi, is, well, if we know this is true, can we come to the conclusion that this is true as well? Not T implies Q, implies P. That's my theorem. Okay. So the first thing we need to do is to negate the theorem. So we need to negate phi, which is the negation of the implication. We apply the definition of implication, and then we apply De Morgan's law. After De Morgan's law, we end up with a CNF already. Does that look like a CNF to you? It's a conjunction of disjunctions, and each disjunction can only have terms from alpha or the negation thereof. Yeah, I mean, not T is a singleton disjunction. I mean, it just has one single thing in the disjunction. Okay, so now we look at the negation of phi, which is the negation of the theorem. We look at psi, which is everything that is known to be true, that you're told that is true, and we combine those two and say, okay, this is the combination. This has to imply false if phi indeed is a theorem. We don't know whether it's a theorem or not, but if it is a theorem, then it has to imply false. We have to get to a contradiction from this conjunction. Is that okay? We good? Or are there any questions? questions? Okay. So now we have this CNF, and we say somehow this implies false. But we need to show that it implies false if phi is indeed a theorem, if not. So this is getting back to the needle in the haystack, right? So because I'm saying that, okay, this is what the needle looks like, and here's a haystack, go find that needle for me, okay? Using the old propositional logic system, the haystack is infinitely large. In other words, just because you have not found the needle yet does not mean the needle is not in the haystack. Okay, and that's one huge problem that we have in the previous system. In the new system, on the other hand, the haystack itself has a limited size. It's finite. It can only be so big. Okay, so that means if I give you a picture of the needle, and so I say, okay, is this needle in the haystack? You can literally do a quote-unquote exhaustive search and confirm one way or another whether that needle is in fact in the haystack or not. In other words, is this phi really a theorem or not? You can now come to an actual conclusion. Even if it is not, you can conclude, nope, phi is not a theorem. Okay, so the next step now is we are applying resolution. Oh, actually, we apply resolution, and can someone tell me what I can resolve in this case? What does resolution mean? I mean, that's about 2 classes ago, so maybe you guys do not remember entirely. But what do I need in order to perform resolution? I need 2 of these terms, okay? 2 terms from the conjunction to share a single variable, where one side has the variable itself, the other side has the negation of the same variable. In other words, if I look at the first expression, I'm looking in the rest of the expressions for P or the negation of R. Okay, both will help me do a resolution. Can we find P in the rest of this entire conjunction novel? Nope. How about the negation of R? Nope. Okay, so the first term cannot resolve with any of the remaining terms. And we look at the second term. The second term has not P or not Q, which means we're looking for P or Q non-negated in the rest of this. Do we find any? Nope. We look at the third term. It's the negation of T. Do we find T all by itself in one of the terms that's following this? Nope. And the last term, since it is the last term, hey, it cannot match anything. So that means we cannot even carry out a single step of resolution, which means we cannot get to the 0 that we want. Does that make any sense? There's no way you can say this can never happen because we cannot resolve to 0. Which basically means, guess what? That phi was not a theorem because we cannot get to the contradiction. But we have a conclusion. This is great. This is massive, okay? Because now we can definitively say that, yep, that theorem that you gave me is not really a theorem. Whereas before, it is almost impossible, right? Because you are looking for something that does not exist in an infinitely large haystack. But now we can actually say, I cannot get to contradiction. There's no way to apply resolution at this point, and therefore, the theorem phi is not really a theorem. So are we doing okay so far with all this stuff? Because I know there are many pieces that you need to connect in order to understand all this stuff, but it is also very important. Are there any questions? Does everybody understand that at this point our conclusion is this particular phi is not a theorem?
Just revolve it around because you cannot prove the negation. That you cannot prove that the negation is a theorem equals to 0.
It does not lead to false.
Yeah.
The negation of the theorem combined with everything that you are told to be true does not lead to false. And that's why, and it's not possible. We know we cannot do any derivation at this point. So that's the conclusion. That's why we can conclude and say that this particular phi is not a theorem. Okay? All right. So, but that's not really helpful because I'm not showing you what is resolution. So we'll go ahead and look at another possible theorem. So this time we have phi prime, which is a different theorem. So phi prime is just saying, okay, what about P implies not Q? Is that a theorem once we know what is known to be true is true? Okay. So what we do is we take the negation of phi. So if phi prime, if phi prime itself is P implies not Q, then the negation of phi prime is the negation of the implication. We apply the definition of implication here, and then we apply de Morgan's law, and then we do some simplification, and now we end up with P and Q being the CNF that represents the negation of the theorem that we want to prove. Is that part okay? Are we okay up to this point? Okay, cool. So now we combine those two, right? We combine everything that is known to be true, which is still represented by psi, and we use a conjunction and combine that with the negation of phi prime, which is now in the form of P and Q. Are we still doing okay so far? Okay. So now we look at this thing here, and we can definitely tell that we can do some resolution. And I choose to be efficient here, so I'm not doing any resolution that is not necessary. So I look at the second term, which is not P or not Q. So we are looking for some other term that has P or Q to resolve with. And this time we got both of those, okay? Now when you get both of those, we can only resolve with one term at a time, okay? So don't try to combine terms and go like, oh, we can do two resolutions in one step. No, just do one at a time, or one at a time. So we choose to combine this not P with this P over here and do a resolution. When you perform quote-unquote a resolution, all you're doing is concatenating the two expressions that is the input, but you're also removing the glue term itself. In this case, the glue term is not P in this expression and P itself in the other term. So that's why we end up with just not Q. Is that okay? This is one step of resolution. So let's slow down and make sure that we understand what is going on. In order to use resolution, you have to find two terms in the conjunction where one term has the non-negative version of a variable, the other term has the negative version of the same variable. Can we find those? Yep, this one has got not P, this one has got P itself. Okay? So when you combine those two expressions, you're concatenating. Okay? Whatever this has and whatever this has, just kind of concatenate everything. Except for the glue variable. In this case, the glue variable is P, so you remove that P variable from the combination of these two expressions. So that's why we only get not Q left. Is that okay? It's a concatenation followed by a pruning of the glue variable. Okay, so think about it in two steps. Three steps. First step is identifying which two expressions can be resolved. Okay? Can we all see that this term can resolve with this term? Because one has the negative version of one variable, the other one has the non-negative version of the same variable. Can we buy that? Okay. Second step, do concatenation. Concatenation means you'll just copy everything and put it onto one huge string, right? So we have not P or not Q, and then we have P or P here. Third step is to trim the glue variable. Whatever variable you're using to glue these two things together, remove all mentioning of that variable, including its own negation. So now we are removing the mentioning of not P and P itself, so you only got not Q left. Is that okay?
Are they like ones that are combined? It's like before you're removing, you're adding, you not P.
I removed them before I combined. But you can look at it in a different way. Yep.
So like if you grab like a step between the two, it would be like parentheses, not P and not Q, or P, and then
Not P or not Q or P.
no, not P and not Q or P, like the combination that's like
These two?
yeah. So like in the first sentence and the second one, there was like a step between them.
In between these two?
Like before you
between
get
the
rid
first
of
and the
P,
second?
Like before you get rid of the P's on the concatenation.
Yeah,
regime.
between step 1 and 2.
Yeah, between step 1 and 2, you'd have not P and not Q or P on like the last term.
Okay, let's go back to the definition of resolution, okay? Because that should help. So let's see. How do I go back to home? There we go. Okay. So we go back to resolution, and this is resolution itself. Okay? So when you look at this resolution itself, it's basically saying if you have two conjunctions connected by a conjunction, okay, and in one you have a sub-expression of psi, the other one has exactly the negation of psi, then you can say that these two, or the conjunction of these two, is implying just the remaining portion of each expression. Okay? So in this case, with this term, we only have phi left. Okay? With this one, we only got rho left. That is resolution. So now you're basically looking at this pattern and apply it to the example that we were talking about.
So it'd be like if it was like, it'd be like if P wasn't there for like the
Correct.
row. Okay.
Yeah, so in the other term, we only got like P by itself, right?
Yeah.
But you can always say P or 0.
Okay.
So there's always the implied or 0 in any expression. Whenever you say, but this is just by itself. Nope, it's never by itself. There's always an or 0.
Okay.
Yep. So are we okay with this? Okay. So let's go back to that example, to the example where there's actual resolution. Okay. Not this one, but this one here. So are we now okay with these two? We are taking this one as the first expression. We're taking this as the second expression. So, but with the tricky part is the P by itself can be seen as P or 0. Okay? So there's always the rest of that disjunction. Okay? So when we combine these two, then we resolve it to just not Q. Because the P annihilates the not P, but the only leftover stuff is not Q itself. Okay? Is that okay? So now we look at the second row, and we go like, can we resolve some more? Yep, the Q can now resolve with the not Q into a 0. Now, how does that work? Because the Q is never really by itself. Q is Q or 0. The not Q is not by itself. It is not Q or 0. So when you resolve those two terms, you have 0 or 0 left, which is why we end up with this 0 here. But because, yeah, go ahead.
I'm just confused on the jump from the first to second row because we're supposed to be taking out the P, right? And then when we go down to the second row, the not P is still there with the disconjunction of not Q.
Oh, I'm just
confused on
calculating.
the.
I'm just adding the terms as we go.
Okay, so it's like there's steps in between. You're just not showing them the steps.
No,
Well,
there
it's
are.
I'm just confused
I
because
think he uses the previous theorem, right?
not Q disconjunction.
Oh, you mean this term here? Yeah, that thing might be a leftover from earlier.
Could you spell out the like this whole thing?
Which thing? Psi?
Steps.
You mean psi? Psi is the same psi as before, so psi is still defined the same way here. I just made the mistake of not removing this term because it was a copy and paste, and I forgot to remove that one.
So we're ignoring that.
Right. So let me fix that right away because I don't like, these things to be half right. this one is pretty close to the end. It's the third term that has the Q or T, not Q or T. So we can just delete this one. I'm just looking whether that looks right or not. Yep, I think that's the one. It's just looking through all the changes, and it only updates the server with whatever has changed. So when we update this, there we go. Yep. Sorry? Because it is actually not done yet. It just took a long time on a slow computer to update all the rendering of the equations. Yes. So I just need to buy a faster computer. This computer, not the server. The server is really fast updating the actual HTML files. These are all expressed in MathJax, which is an extension to display mathematical equations. The nice thing is it's very scalable. You can actually magnify all the way, and there's no pixelization because it's actually drawn or rendered, using the curves. But the bad part is it's more compute intensive than just displaying a picture. Okay, so is that better? Okay. So because we have this conjunction with a 0, so the whole thing is false, which means phi prime is indeed a theorem in this case. Are we okay so far? Yes? Okay. Now remember, how I said, in this particular case, if everything is expressed as a CNF, a conjunctive normal form, the haystack is fixed. Okay, it cannot exceed a certain size. Remember I said that? Okay. So let's figure out why that is the case, and what is the worst case that can happen. Okay. So let's say we have P, Q, R as 4 variables. Okay? Okay. There we go. So we have 4 variables. So now we think about each subterm of the CNF. In other words, how many ways can we generate disjunctions out of just either a variable or the negation theorem? Okay? So what do you think? Okay, if you think about P, okay, how can we have P in a disjunction in the CNF? Okay, P can be P, P can be not P, and P can be absent. It's not even there, right? So there are 3 options for the variable P. There are also 3 options for the variable Q, because Q can be in a disjunction, not Q can be in a disjunction, or a disjunction does not mention Q at all. Okay? So the rest you kind of know already, which means we got 3 options for the first variable, 3 options for the second variable, 3 options for the third variable, 3 options for the fourth variable. You multiply these, and we got 81. In other words, with 4 variables, there are only 81 possible disjunctions they can make out of it. Okay? Now I know it is still a pretty big number. Okay? It's 4 to the power of 3, basically. So the number of variables to the power of 3 tells you the total number of possible disjunctions they can generate out of it. Huh? 3 to the power of 4. Yes, 3 to the power of number of variables. So it is exponential. We don't like those the order of magnitude, but it is finite. The bottom line is it is finite. Okay? So if the CNF that you do a resolution with can only have a finite number of disjunctions to begin with, it will only take a finite number of steps to come to one of two possible conclusions. We got to 0, woohoo! You got your theorem. Or 2, I cannot resolve this any further. No matter what I do to do the resolution, we only got terms that is already in the original expression. You can only get to only one of those two answers. Whereas the first one tells you that, yep, the theorem that you suspected was a theorem is in fact a theorem. The second one says, nope, it's not a theorem. But it can be done within a finite amount of time, unlike the open-ended propositional logic system where you can go in the wrong direction indefinitely and never know whether the theorem that you're supposed to prove is really not a theorem or we just haven't gotten there yet. So is that okay? I mean, do you guys understand the significance of this approach compared to the original approach, which is, oh, we'll just do everything that we can humanly do, using logic, but that can send you in the wrong direction forever, and you can never really end up proving something. Yep.
It's gonna be a slight question, but what are the question marks supposed to be?
The absence of.
Oh, the absence.
Lack of. It's really hard to represent it, the lack of, right?
What's the difference between that and negate?
Negation means the negation itself is true.
Okay.
The absence of, you can kind of the absence of as a 0. I mean that's
always 0.
yeah. So for each place you get these options, right? So you can have, because anything or 0 is just anything, so it's the same thing as not specifying it.
The question marks, not the commas?
Huh?
I was confused by his question. It was the question marks are 0, not the commas.
The question marks are now replaced by zeros. In other words, okay, so let's make this a little bit simpler because I don't want to enumerate 81 rows. I mean that's not a good use of time. Okay, so let's say we only got 2 variables, P and Q. Okay, so how many disjunctive expressions can I generate out of just 2 variables? Okay. So we have P, Q, we got not P, not Q, and each one can be a 0 as well. So we are now looking at the, guess what? Cartesian product between these two. So we can have P or Q, we can have P or not Q, we can have P or 0, we can have not P or Q, not P or not Q, not P or, oops, not P or 0, and then we have 0 or Q, 0 or not Q, and then we have 0 or 0. I mean that's it. You only got 9 possible cases. I mean any one of these can be inside the big conjunction, but the largest conjunction you can possibly get is really just the conjunction of all of these things. It's finite. You cannot get any bigger. So when you look at the well-formed formula space, in this case, when you only have 2 variables, it's a pretty tiny space. Is that okay? More or less? Okay. The important point is it is finite. There are only so many dots in that space. And certain dots are labeled red to begin with. But the resolution step, the resolution process, is not looking for something that is true. It's looking for something that is false. So are we okay so far? What if I ask you guys to write a C++ program to perform resolution? How would that, what kind of logic is it going to include? Okay, what kind of representation are you going to use? to, okay, what are you going to use to represent a disjunction, a single disjunction? How do you represent it?
Or, isn't it?
Well, it's a whole bunch of ors, okay? But you need to be able to generate those expressions, so it cannot be just or, you know, in C and C++. I'm looking for a data structure that can be used in order to say, oh, okay, this disjunction is P or not Q or R. Okay, how do we express that?
If else, maybe?
You can use, there are several ways to do it, okay? The most expensive way to do it is to use an array of characters per disjunction, okay? Okay, so let's say we're dealing with P, Q, R, you know, 3 possible variables. So then you define char disjunctive expression, and in this case, you don't need a null terminator because you know the length is only going to be 3. Is that okay? So the null terminator is not really needed until you print something out, otherwise it's not needed. Okay. So now for each one, you can say, okay, so let's say we want to express P or not Q or R, okay? Or not R. There we go. So you can now say DE bracket 0 is just P, DE bracket 0, bracket 1, sorry, the second element, is the negation of Q. So you need to find a way to represent negation. There are many ways to do it. You can always say uppercase is negated. Okay. You can have DE2 then equals to uppercase R. So these are all characters. So this is how you can very wastefully encode this disjunction form into an array of characters. Okay. What if we want to do something like this? What if the whole disjunction is just P by itself? The other 2 terms are just completely missing. Okay, so you can represent it like this. Okay, DE0 is lowercase p, DE bracket 1 is a 0. Okay, because it's just or 0, so we can use 0 here. DE bracket 2 is also a 0 because we are not mentioning R at all. So is that okay? Do you guys see how you can quote-unquote encode a disjunction just using an array of characters? So now, you know, how do you do resolution? You basically have a whole bunch of these arrays of 3 characters, and it's just a matter of matching, right? Okay, you're saying, okay, I know this one has a P, I'm looking for something else that has uppercase P. Because if something else has an uppercase P, those 2 can now resolve. Is that making any sense? So what are you doing when you're resolving? Well, you're just saying, okay, besides P, what else is here? And then with the other one, besides the uppercase P, what else is there? And you just combine them. That's one way to do resolution. But you can see that coding this engine, the resolution engine, is not really that hard. I mean, we are talking about the kind of coding that you can do without taking cisp440, nor 400. This has nothing to do with object-oriented programming. It really is just a nested loop, and keep checking. Okay, I'm looking for a particular character here, and the uppercase of the same character over there. Is there a match? No, move on, next one, and so on. When you do find a match, combine those 2, make a new term, add it to the array of arrays, and then you'll just continue the process until you either get to 0, 0, 0 in an array, or you can say, oh, I cannot add any new terms because everything that I can resolve is already there in the entire array. That can be done before next class. So here's your challenge. Use any programming language of your choice. PHP, Perl, Python, whatever, okay? JavaScript, and get this done by next Monday.
Extra credit.
Too simple. But I want you guys to do it mechanically, because when you program it, then you actually understand the mechanism a lot better. Okay, so it's an exercise. It's not going to be graded. There won't be any credit for it, but I think it is beneficial.
I'm still confused on why you're allowed to add and why to go back. Why are you allowed to add that not Q there? You said that because the P is what binds these two expressions together. But I'm still confused as to why you're allowed to add the not
Okay,
Q.
so do you remember the